means is that whenever you have the gas molecule, the average kinetic energy is the same, provided that all the gas molecules they are ideal gas. So if they are ideal gases, then they all have the same the average kinetic energy, provided that they have the same temperature. So that's the important thing about this. Okay, and so now since we know the average kinetic energy, what we want to know is that how much energy is contained within the system. So how much energy is contained within the system, really what we can do is that we would, let's say each molecule, if we're talking about monatomic, gas molecule, so it has the most simplified form. It can only move in the three directions, the x and y and z directions. So for monatomic gases, what is the energy or the internal energy of the system when you have m molecules? So let's say you have m moles of the monatomic gases. Okay, so what is the kinetic? What is the monatomic gases? What is the internal energy of that system? So in order to find out that internal energy, we know that because for monatomic gases, the only way to store energy will be in the form of kinetic energy. So in that case, we can say that the internal energy of the system is equal to, let's say, there are m particles, the total number of m particles, and then each particle, and then multiplied by the average kinetic energy. Okay, so in that case, and we know that this capital M basically is equal to, so your capital M here would just be the number of moles and then times the Avogadro's number. So that will be the total number of particles. And that's it. We know that the average kinetic energy is, is 3/2 kT. So we can actually calculate the amount of energy contained within that system if there are capital N number of particles. You have your capital M here, you have your 3/2, and then you have the Boltzmann constant, and then you have the temperature. So rearrange this, we know that n times k. What is n times k? N times k basically, so we're going to replace our capital N with this. So what we have is that the number of moles times the Avogadro's number, and then times 3/2, and then times k, and then times T. So what we have here is that you have the Avogadro's number times the Boltzmann constant. That will give you the gas, the gas constant. So what we have is that will be 3/2, and then times number of moles, and then times your R, and then times your T. Okay. So again, what does that mean? It means that the internal energy of the system again only depends on the temperature of the system. Okay, so regardless what kind of gas molecule you're dealing with, provided that they are all monatomic gases and they are ideal gases, so it only depends on the temperature. Okay, so this is an important result. Regardless what kind of species you're working with, it all takes up this form. So if this is the internal energy of the system, that's 3/2 n times n times T, then the change in internal energy would just be determined by the change in temperature. So you will have 3/2, and then you have your N, you have your R, and then you have your T. Okay, so that's basically an important result, and that only and we can see that previously we mentioned that on last week we mentioned that there are a couple of state functions that does not depend on the process, but it only depends on the initial or the final position or the location. So this is basically what it means. So your temperature, how do you get from point I to point F in order to get to the temperature difference? It doesn't really matter. so long as you have the same temperature change delta T, then the internal energy change will stay the same. Okay, so that's that. So the next thing we want to know is that given we know that the internal energy only depends on temperature. We know that the average kinetic energy only depends on temperature as well. So let's say we want to look at on the PV diagram. If we have the gas molecule that undergo some sort of a thermodynamic process, we want to find out, how the utilize the first law of thermodynamics. How do we calculate work? How do we calculate heat? And what is the change in the internal energy? So, for example, let's say on the isotherm, on the PV diagram, we can have two isotherm. So the first one here, isotherm, of course, is the points the points that all have the same temperature. We connect it together. And then this one is upper one, and then we have another one that's right here. Okay, so let's say this one has a temperature T, and this one has a temperature delta T. So it's a little bit higher, okay, and the temperature difference is delta T. So let's say if we want to, let the monatomic gas molecule. So again, we utilize the most the simple case, monatomic. When I say monatomic, of course, it's just that one single atoms. Okay, so that's it. We have monatomic gas, and then we let the gas go through a thermodynamic process that is at a constant volume. So we're keeping volume as constant. So the question is, how do we calculate heat involved during this constant volume process? So that's it. Initially, this is the initial point I, and this is the final point F. I will let it go from point I to point F, keeping the volume constant. So you can see that this, from point I to point F, the volume is kept constant. How much energy is involved in the heat transfer? How much work is done? How much work is done by the gas? And what is the change in internal energy? So who can answer me that how much work is done during this constant volume process? Come on, how much work? How much? Yes, zero, right? There will be no work because work is, if you remember, work is defined as PdV. If your V is kept constant, of course, this has to be zero, right? So no work is done. Okay, so now what about heat? For constant, so okay, so what about heat? How much work is involved during this constant volume process? So how do we calculate? What would be the expression for constant volume process? Now we mentioned that work is very process dependent. So is heat. So all this, they all depends on the process. So for constant volume process, what we're going to, we can use the same analogies when we're dealing with the gas, with the solid. If you remember, previously on in chapter 28, chapter 18, when we talk about the liquid or solid when it goes through, when there's a temperature change, then there's a heat transfer. So if you remember, Q is equal to mc delta T, so involves the mass of the object, the specific heat of the object, and then times the temperature change. So now we're dealing with the gas. We're going to use very similar expression. Instead of using the mass, we're going to use the number of moles. Instead of using the specific gas, specific heat, we're going to use a specific heat at constant volume. And then there's also the term that involves the change in temperature. So in that case, the heat transfer during this constant volume process will be the number of moles times specific heat, but now we have to specify the process. So we say that constant volume, specific heat at constant volume, and then times your delta T. Okay, So this is when you have a constant volume process. The amount of work is 0. The amount of heat transfer is mCv delta T. This is always true. Okay. So now we want to see how much change is involved in the internal energy when when the gas is going through a constant volume process. So now if we use this expression, so the change in internal energy, we're going to use the first law of thermodynamics. The change in internal energy is equal to Q minus W. Okay. So now we're going to substitute your Q with this expression. So you have your NCV, and then times delta T, and then minus amount of work done by the gas is 0. Now, what about on the left-hand side of the equation? What is the change in internal energy? Can you take gas? What is the change in internal energy when there's a temperature change delta T? The energy change is equal to the temperature change is proportional to the temperature change. Now that's flip back to the previous page. See, this is the change in internal energy. That's 3 halves nR delta T, and that is regardless. This is for monatomic. For monatomic, gases, the change in internal energy is always 3 halves nR delta T. Okay, so this is for any process. In other words, such a is a constant volume process, constant pressure process, constant whatever, or a divided process, whatever. As long as there's a temperature change delta T, then this is internal energy change, provided that the gas you're working with is monatomic. Okay, so in that case, 3 halves nR delta T. So we're going to set on the left hand side equation that 3 halves and then nR delta T. So you can see this has to be equal to that. And then they all have the delta T, so that get cancelled. They all have the number of moles that get cancelled. So what we have now is that your CV, specific heat at constant volume, that equals to 3 halves R. Okay, and we know the R value, which is the gas constant. So this is equal to 12.5 and the unit is joules per mole per Kelvin. So again, I want to caution you that your CV is equal to 12.5, 12.5 joules per mole per Kelvin. That is for monatomic. You'll learn later that for different gases, like molecules, your CV value will change. Okay, it will be it will be it will be proportional to R, but nevertheless, you will not be always 3 halves. 3 halves is only for monatomic gases. Okay, any questions so far? So now we know that your CV value is 3 halves R. So what we can express the change in internal energy, or the internal energy can be expressed in terms of the specific heat at constant volume. So in other words, not this, but anyway, so internal energy, your internal energy can be expressed as CV. So you have 3 halves R, which is just CV. So you have your little n here, the number of moles times your CV, and then times temperature. Okay. So this basically tells you that for any process, internal energy has to be in this expression, which is the number of moles times the specific heat at constant volume and times the temperature. So if there's any change in internal energy, then your T becomes delta T. Okay. So this is for, this is when you have a constant volume process. Your Q is NCB delta T, and the change in internal energy and the internal energy is this form. So now that say we're using the same, on the same PV diagram, but now we're going to take the gas to through a different dynamic, thermodynamic processes. Now, instead of keeping the volume as a constant value, now we want to keep our pressure as constant value. So now let's say if we, let me just draw it here. So let's say if this is my starting point I, and this is my final point F. So we're going to let the gas go through this, keeping the pressure as a constant. Okay. So pressure now is constant. So again, we are still working with the monatomic gases. So P is constant. So now again, the important question we want to ask is how much work is involved when the gas is going through this constant pressure process, and how much heat is being transferred, and what is the change in internal energy. Whenever we're dealing with the a cycle, whenever we're working, with the PV diagram, these are the questions we want to know. These are the questions we want to ask and the answers to find. So how much work is being done by the gas when you have a constant pressure process? How much work? So your pressure now is a constant. Now what is defined as PdV? So now your pressure is constant, so you can move your P, to the outside the integral. So then the amount of work would just be the change in volume time. The change in volume is proportional to work, or the work is proportional to the change in volume. So in other words, that will be pressure times delta V. This is the amount of work that's being done by the gas. What about the amount of heat? The amount of heat that's being produced, that is the amount of heat that's being transferred. What would be the expression for the amount of heat at constant pressure? So again, we're going to use the NCV delta T. That's our same expression. So you have. So what kind of expression would you have? So you have the number of moles, and then specific heat, but now it is at constant pressure, and then times the change in temperature, delta T. So this will be the expression for the heat transfer during this constant pressure process. So it's NCP delta T. So now we have work, we have heat, so we can find out how much change in internal energy. So again, for constant volume process, for constant pressure process, what is the change in internal energy? What is the change in internal energy for constant pressure process? So is your microphone working or no? Can you speak or you have to type? Okay. It was the source of the problem. Oh, okay. No, but he minus work. Well, what will be okay? Okay. Do you remember? Let's go back to the previous page. And another one. Do you remember when I mentioned something that the change in internal energy is always NCV delta T for any process. For any process, it always takes up this form. So it doesn't really matter what kind of process, constant volume, constant pressure, adiabatic, or cyclical, it all takes up this form. That's NCV delta T. Okay, so now let's go back to here. So the change in internal energy is always NCV, and then previous page we mentioned that the change the internal energy is NCVT. So the change in internal energy will just be NCV delta T. So for any process. So now we can have this is just NCV and then delta T. Okay, so this is change in internal energy. Now, of course, this also has to be equal to Q minus W because that's your first law of thermodynamics. Okay, so now what we're going to do is I set this equal to this. So you have your NCV delta T that's equal to your Q. Your Q is NCP delta T and then minus W. Q is your P and then delta V. So you can see that on the left hand side we have NCV delta T, on the right hand side we have NCP delta T, and then minus P delta V. So if we can express your delta V in terms of delta T, then they all have the common delta T. Then you can remove delta T in the equations. So let's say if we can do that. Let's say PV equals nRT. That's your ideal gas law. Okay. So for this, if we already know that well, at the constant pressure, so if you take the change in every turn, so you have your P is a constant, and then times delta V, and that has to be your N R and then delta T. And so what we can do is that we replace. So on the right hand side, you have your NCP delta T, and then minus your P delta V, that's your NR delta T. So your delta T cancel, delta T cancel, delta T cancel, your N cancel, your N cancel, N cancel. So what's left is that your CV is equal to your CP minus R, one gas constant. So we arrange this, what we get is that the specific constant pressure is equal to your CV, the specific constant volume, and then plus 1, okay? So CV, if you remember, for monatomic gases, CV is 3 halves R. So your CP now, 3 halves R plus 1 R, that gives you 5 halves R. Okay? So as you can see, your CV value and CP value depend on what kind of gas molecule you work with. For monatomic, CV is always 3 halves R, CP is always 5 halves R. And then for other gases, then your CV and CP will change accordingly, right? Any questions so far? So the important thing is that CP and CV, they are equal to this. Okay? Any questions so far? All right, so now I mentioned earlier that your CP value, your C value really depends on what kind of gas molecule you work with. Okay, so that involves a concept equal partition, equal partition of energy. Let's say for monatomic gas, what are the monatomic gas? Let's say hydrogen, atomic oxygen. Can you give me an example of a monatomic gas? Just give me any species. Okay, like nitrogen, okay, or helium, all this, they are monatomic gases. Okay, so for monatomic gases, your CV value is 3 halves R. And of course, you can calculate your CP just by your CP is always equal to CV plus R. So we don't even need to worry about what CP value is, because as long as you know your CP value, then your CP value can be calculated easily. All right, so these are the monatomic gases. Your CV value is 3 halves R. What does that tell you? We mentioned that for monatomic gases, the only way for the monatomic gases to have energy is that it is stored as in kinetic energy. Okay. Now for kinetic energy, there are 3 dimensions. You have x, y, z. So that's why your 3 here represents 3 directions that the particles can have. It can move in those 3 directions. So your CV now is 3 halves R. That represents 3 different possible 3 possible way for the atoms to store energy. Okay, so what about like diatomic? What are the example for diatomic gases? Okay, so O2, N2, and monatomic gases, N2O2, let's say what else? H2, right? All this, molecule, O2, N2, and then H2. These are, okay, C6. What's that? That's carbon 6. It's not monatomic, diatomic. Diatomic, which means that they only consist of 2 atoms. Okay, so as long as you have like a molecule that has 2 atoms, okay, so it's 2 atoms. So let's say O2, N2, and H2. Those consist of two atoms that form a molecule. Then your CV value now becomes 5 halves R. The reason is that now, in addition to the X and Y, Z directions that you can store energy, there's 2 additional possible ways for the molecules to store energy. That will be in rotation. You can have the X, Y, rotating along the X, Y axis or along the Y, Z axis. So these are, along these 2, the central axis. So you have the 2 additional ways to store energy. Okay. So now, of course, CP. So you can see that for monatomic, it's 3 halves R. For the diatomic, is 5 halves R. So your CP value will change as well. So now your CP value for this one, for the diatomic, that will be. So let's see. Let me just write it down here. So your CP here would be 7 halves R, right? For the diatomic. Okay. So what about when you have a molecule that consists of more than 2 molecules? Let's say polyatomic. For example, let's say CH methane is more than 2 molecules, and of course there are other there are other compounds that involves more than just like 2 molecules. In that case, I mean, I'm sure there are many examples, but I can't. I mean, more than just 2 molecules. So let's say when you have a polyatomic, okay, that's more than 2 atoms, forming the molecules. Then what is the specific heat then? In that case, in addition to 2 then it's just like it will not just be 2 direction for rotation. There are actually 3 different directions for rotation. So now you have 3 that's in X and Y, Z axis, and then you have 3 that can rotate freely. So in that case, your CV now is equal to 6. 3 plus 3, so that's 6 halves, and then R. Okay, so in that case, your CP value, of course, plus 1 R, that will be this, and then times your R value. So what it means is that you can see that your CV value is proportional to 3, 5, or 6. Okay, so and that number, this 3 represents X and Y, Z direction. This 5 represents X, Y, Z direction plus 2 rotation, 2 direction for rotation. And this 6 represents 3x, 3, the Cartesian coordinate X and Y, Z, and then 3 rotation along the axis connecting these atoms. So this is what we call so all this is what we call the equal partition of energy. Each direction has 1/2 R of energy, and then depending on how many directions, how many possible ways for the atoms or molecules to store energy, then you have to change your CV value, this value in the numerator, accordingly. Okay. All right. So that's so far what you would so whenever you do a problem, you have to make sure make sure that you're dealing you have to make sure you know which species you're working with, either diatomic, monatomic, or polyatomic, because your CV value will be used you will have a different values. Okay. Any questions so far? Okay. So we talk about, if you look at previous page, these are these are for the you have two isotherms, and then connecting these two isotherms, you can either go through the constant pressure process or constant volume process, or you can go through any other process. Now, what about when you have a process that's that's adiabatic? For example, this is your PV diagram. Okay, so these are the two isotherms. What will be the shape for the adiabatic process? For adiabatic process, what we know is that it will have. Let's see if I can have a different color. What we have is that it has a steeper slope. So what you have here is like this. This is what we call the adiabatic. Okay, so this curve is adiabatic. What does that mean when I say you have a process that's adiabatic? Whenever you see the word adiabatic, what does that mean? The heat, not heat equals to 0. Heat transfer is 0. There's no heat transfer. Okay, heat does not have a value of difference. That makes sense. So the heat transfer is 0, which means that your Q, heat transfer, is 0. All right. So in this case, whenever you're dealing with an ideal gas that's taken through an adiabatic process, in addition to the PV equals nRT equation that you can use, there's 2 additional equations you can use as well. We're not going to derive it, but I'm just going to give it to you. So for ideal gas, we know that for any process for an ideal gas, PV always equals nRT. That's for any ideal gas. Okay. Now, if the gas is going through a adiabatic process, then there's 2 additional equations you can use. One is that P times V, and then to the gamma, is a constant. What does that mean, to the gamma is a constant? It means that, say, initially you're at point I, and then go through a adiabatic process to this point, that's your F, then your PI, the value here and the value there, and then VI to the gamma is equal to your PF. This is your PF, and then this is your VF. So you will have your PI VI to the gamma is equal to PF times VF to the gamma. So you might ask, what is gamma? So gamma is basically the ratio of specific heat. So your gamma here, your gamma is equal to Cp over Cv. So again, you can see that because for different gases, your Cp and Cv value will be different. So what is gamma value really depends on whether you're dealing with diatomic, monatomic, or polyatomic. So can you give me my gamma? Can you give me a gamma value for monatomic? If you're dealing with a monatomic, what will be your gamma value? Anyone? If this is monatomic, what is the ratio of gamma? 5/3. So 5/3, right? That's your gas. That's your monatomic gas. What about diatomic? For diatomics, the ratio is 7/5. So that's 1.4. Okay, so we can see that when you're dealing with monatomic or diatomic, your gamma value will be different. So this is one equation, PV equals nRT, that's always true for an ideal gas. This is another equation when you're dealing with a adiabatic process. And then if we can, if you express pressure in terms of volume, and then this equation can be there's another equation that can be used as well, which is the initial temperature times the initial volume, but now is gamma minus 1. The power is gamma minus 1, and that is equal to your TF, and then times, and then to the gamma minus 1. Okay? What it means is that, whenever you're dealing with a adiabatic process, you have 3 equations that you can work with. So, so when you're dealing with the engine problem, which is, the topic of on chapter 20, then we're going to utilize all these equations when you're dealing with the engine. Because some of the engines, require a adiabatic process, and then these are the equations that you can use to do that. Okay. Now, just one thing I want to mention before I close this is that in chapter 18 we talk about free expansion. Now we mentioned that free expansion because it happens so fast. There's no time for heat exchange. So for free expansion, it is adiabatic because no heat exchange, and there's no work is being done because it happens so fast. There's no pressure, so gas does not do any work, and so there's no changing internal energy because using the first law of thermodynamics, you have Q equals to 0, you have your W equals to 0, of course your internal energy has to be equal to 0 as well. So you might wonder, for a free expansion process, can you use these 2 equations? Because for free expansion it is adiabatic. Can you use these 2 equations when you're dealing with a free expansion? Now, for the free expansion, this is an exception. Although free expansion is an adiabatic process, but these 2 equations cannot be used. The only equation you can use will still be the ideal gas law. Only this equation can use PV equals nRT. You cannot use this, and that is because for free expansion, this equation do not apply. Okay, so the situation is a little bit different. All right. So as you can see, the only equation that is working for all processes will be just the PV equals nRT for ideal gas. All right. So I think I'll stop here, and so I'm going to actually stop the recording so that it does not take up a lot of space.